Suppose we're given ay double prime plus by prime plus cy equals 0, where a, b, and c are real numbers and a doesn't equal 0. This is a second-order linear differential equation that is homogeneous. The set of solutions to this differential equation forms a vector space, and we want to look for a basis for this vector space. Now, again, this is a second-order differential equation. If we find two linearly independent solutions to ay double prime plus by prime plus cy equals 0, we will have found a basis for this vector space. Now, to find these solutions, here's the idea. Think of a function so that when you take the first and second derivative, it doesn't change very much. And ideally, we're going to try y equals e to the rx. By the chain rule, we know that y prime is re to the rx and y double prime is r squared e to the rx. If we make our substitution into the above differential equation, we get the following. ar squared e to the rx plus br e to the rx plus ce to the rx equals 0. If we factor out an e to the rx, we get the following. E to the rx times the quantity ar squared plus br plus c equals 0. Okay. Now, e to the rx is never 0. So that says ar squared plus br plus c equals 0. Now, suppose r1 and r2 are solutions of ar squared plus br plus c equals 0. We have three cases for r1 and r2, but in this video, we're only going to consider two of them. I could make a separate video for the third case. Now, in case 1, suppose R1 and R2 are distinct real solutions of AR squared plus BR plus C equals 0. Y1, which is equal to e to the R1x, and Y2, which is equal to e to the R2x, are linearly independent solutions of ay double prime plus by prime plus cy equals 0. Now, these are two linearly independent solutions, and what does that mean? That means I can't find a number to multiply by y1 to produce y2, essentially. So if y1 and y2 are two linearly independent solutions, then any linear combination of y1 and y2 are, or is, a solution of ay double prime plus by prime plus cy equals 0. In other words, if I take y1 and multiply it by a, and y2 and multiply it by b and add them, that's a solution to this differential equation. So it's essentially what I'm saying on the next page. Y equals ae to the r1x plus be to the r2x is also a solution. It's the general solution. Now, with that in mind, let's take a look at an example. Suppose I want to solve 2y double prime plus 3y prime plus y equals 0. Set y equal to e to the rx. That's going to be our first step consistently. Y prime is re to the rx, and y double prime is r squared e to the rx. If I make my substitution, I get 2r squared e to the rx plus 3r e to the rx plus e to the rx is equal to 0. If I factor out an e to the rx, I get e to the rx times the quantity 2r squared plus 3r plus 1 is equal to 0. But again, remember, e to the rx is never 0. And so that says 2r squared plus 3r plus 1 is equal to 0. Now, if I factor, I get 2r plus 1 times r plus 1 is equal to 0. By the zero product property, we can say that r equals negative 1/2 or r equals negative 1. Now remember, what's the goal? We want two linearly independent solutions to this differential equation. Well, y1, which is equal to e to the negative 1 half x, and y2, which is equal to e to the negative 1x, are those two linearly independent solutions. We can show that, okay? So the general solution looks like y equals ae to the negative 1 half x plus be to the negative x. Example 2. Suppose we want to solve y double prime plus 5y prime plus 6y equals 0. Set y equal to e to the rx. Y prime is re to the rx, and y double prime is r squared e to the rx. If I make my substitution, I get r squared e to the rx plus 5r e to the rx plus 6e to the rx is equal to 0. And I'm going to factor out an e to the rx. And when I do, I get e to the rx times the quantity r squared plus 5r plus 6 is equal to 0. But e to the rx is never 0. And so r squared plus 5r plus 6 must be 0. And if I factor, I get r plus 2 times r plus 3 is equal to 0. So r is negative 2 or r is negative 3. So my two linearly independent solutions to this differential equation are y1, which is equal to e to the negative 2x, and y2, which is equal to e to the negative 3x. Those are my two linearly independent solutions. Again, remember, that's the primary goal. You're trying to get two linearly independent solutions. So my general solution will be y equals ae to the negative 2x plus be to the negative 3x. And that's example 2. Now let's take a look at case 2. R1 and R2 are solutions of ar squared plus br plus c is equal to 0, where r1 and r2 are the same. Now, y1, which is equal to e to the r1x, is a solution of ay double prime plus by prime plus cy equals 0. Okay. Now, if I let y2 equal e to the r2x, yes, that's a solution to this differential equation. The problem is that y1 and y2 are not linearly independent. So saying y2, which is equal to e to the r2x, would not be sufficient. It turns out that we can show y2, which is equal to xe to the r2x, is a solution of ay double prime plus by prime plus cy equals 0. Additionally, we can also show that y1 and y2 are linearly independent. And so the general solution will look like y equals ae to the r1x plus bxe to the r2x. And the one thing I want to stress is that r1 and r2 are exactly the same. And let me write that a little clearer here. r1 is the same as r2. Okay. Let's take a look at example 3. Solve y double prime minus 4y prime plus 4y equals 0. We're going to do the same process, if you will, as we did in the first two examples. So the first step is we're going to set y equal to e to the rx. Y prime is re to the rx, and y double prime is r squared e to the rx. If I make my substitution, I get r squared e to the rx minus 4r e to the rx plus 4e to the rx is equal to 0. If I factor out an e to the rx, I get e to the rx times the quantity r squared minus 4r plus 4 equals 0. And again, remember, e to the rx is never 0. So what that says is r squared minus 4r plus 4 is equal to 0. if I factor, I get r minus 2 to the second is equal to 0, which says r is equal to 2 twice. Remember, it's a quadratic equation, so you need two solutions. It just so happens is that the solutions are duplicates of each other. So what's the goal in solving this differential equation? We need two linearly independent solutions. My linearly independent solutions are y1 equals e to the 2x and y2, which is equal to x e to the 2x. Those are my two linearly independent solutions to the differential equation. And so my general solution will look like y equals ae to the 2x plus bx e to the 2x. And that's how we do example 3. In example 4, suppose I ask you to solve. Doesn't matter, right? If I have 4y double prime minus 4y prime plus y equals 0, the process is going to be the same. So I'm going to set y equal to e to the rx. Y prime is re to the rx. Y double prime is r squared e to the rx. I'm going to go ahead and make my substitution and get 4. I'm replacing y double prime with r squared e to the rx. So I get 4r squared e to the rx minus 4, replacing y prime with re to the rx. So I get minus 4r e to the rx plus e to the rx is equal to 0. So I'm going to factor out an e to the rx. And when I do, I get e to the rx times the quantity 4r squared minus 4r plus 1 is equal to 0. E to the rx is never 0. So 4r squared minus 4r plus 1 equals 0. And if I factor, I get 2r minus 1 to the second equals 0. So therefore, 2r minus 1 equals 0. And if I solve for r, I get r equals 1/2 twice. So y1, which is equal to e to the 1/2 x, and y2, which is equal to x e to the 1/2 x, are two linearly independent solutions. Okay? These are linearly independent of 4y double prime minus 4y prime plus y equals 0. So once we have our two linearly independent solutions, we can write our general solution. It's going to be a linear combination of y1 and y2. So in other words, y equals ae to the 1/2 x plus bx e to the 1/2 x. And that'll do it for this video. This is a video on solving second-order linear differential equations that are homogeneous. And we looked at 2 cases and 4 examples. Okay, thank you.